And Andy, please take it away.
Okay, yeah, thanks, Sam. Yeah, so this work I'm presenting, the question we asked ourselves is how you can compare Markov chains, their convergence rates, in particular in the situation where one of the convergence rates could be subgeometric as opposed to exponentially fast. And the key tool we introduced in this work to do that is this idea of a weak Poincare inequality, which I'll describe. And the particular application we had in mind was to pseudo-marginal methods. So the setting of this talk hopefully will be the nice familiar one of MCMC inference, where you want to get samples from pi, say, to evaluate some integral. And you're going to do that by building a pi reversible Markov chain, which happens to be ergodic. So you can just use the sample paths to approximate, well, the distribution pi. And of course, the quality of this estimator based on empirical averages along the sample path will depend upon various things, including, for example, how fast the chain converges to equilibrium. And of course, our favorite way to build a pi reversible Markov chain is to use Metropolis-Hastings, where, of course, you have a fixed proposal distribution, which you use at each iteration, and then you accept or reject the proposal with a given probability at each step. And here I've just highlighted in blue how the target distribution, how the target density pi enters the picture, right? It's just pointwise evaluation in this acceptance ratio at each step. So provided you can do that, you can just run this thing, no problem. And for this talk, just to be concrete, we'll just focus on like random walk proposals. In our actual paper, it's more general than this, but just to be concrete for this talk, we'll focus on this case of random walk. And so for random walk Metropolis, various things are known. And in particular, if you're interested in looking at when do you have exponential convergence, it's closely related to when you have an exponential moment. So it's not quite if and only if. Anthony recently pointed out to me the if direction is a bit more subtle. You need an exponential moment plus a mild drift condition. But certainly you need to have an exponential moment if you want to have hope of exponential convergence. But of course, there are various densities which don't quite fit so neatly into this framework. So for example, something like this pi here, which is still pretty simple, admittedly, you can't just straightforwardly do random walk Metropolis on this, not because of any issues with the tails, but because it itself can't be evaluated straight away, right? If I gave you an x, it's not obvious immediately how you evaluate this because, of course, there's an integral in the definition of pi. And so although you can't straightforwardly evaluate it pointwise, our hope is not lost, of course, because you can think about this form. It's kind of like you have a latent variable z, which is like a centering parameter, which itself has a normal distribution. So because of this relatively simple form, you can still certainly construct an unbiased estimator of pi simply by simulation, right? You simulate some z from the marginal distribution, which is normal, and then just consider e to the minus x minus z cubed, where z is the simulated value. And certainly up to a constant, which is not going to be a problem, you have a non-negative unbiased estimator pi hat of the original pi of x you wanted. And so what you can do then is you can just plug that into your original Metropolis-Hastings, because remember the original pi of y and pi of x you couldn't evaluate, but you can just use your unbiased estimator instead. And the miracle of pseudo-marginal Metropolis-Hastings is that if you just run this algorithm where you've replaced pi with pi hat, is still a valid scheme that targets pi. So the inference you'll do using this algorithm will still be valid in the end. And I really think it is quite a miraculous result. The way you prove this is just by considering an augmented state space, which contains all the randomness you need to generate these pi hats. And I'll come back to that a bit later. And so that's great. So that gives you a way to use, random walk, say, in situations where pi isn't itself pointwise, available, but you can construct a non-negative unbiased estimator. But of course, certainly on an intuitive level, you'd expect this algorithm to do worse than the original Metropolis-Hastings, where you just had a pi, right? Because you can think the information that's encoded into pi has been kind of smudged by an extra factor, because you have an approximation of pi itself rather than pi. And so a really natural question you could ask is, well, how do you quantify, the loss in performance when you use the pseudo-marginal chain with an unbiased estimator as opposed to the original one? Right, and of course, unbiased estimators come in all shapes and sizes, right? You can have a very good unbiased estimator that has a very low variance, which is practically pi of x itself, or you can have a horrendous unbiased estimator with a really fat tail out at infinity, with a huge variance. You'd intuitively expect that to be much less good. And so a first answer to this question of how much worse is pseudo-marginal compared to the original marginal Metropolis-Hastings chain was given in this paper of Andi from 2015, where they basically said, well, if you consider your unbiased estimator pi hat as a perturbation of the original one, so just a pointwise perturbation multiplied, where this W is a non-negative random variable with expectation 1. Well, what you can say in that situation is, well, if you assume for starters that the marginal chain, just a pure random walk targeting pi exactly with no pi hat, if that was exponential, and if these weights Wx are uniformly bounded, so there's just some universal constant that will always upper bound your weights, then the pseudo-marginal chain will still be geometric. So that will still have exponentially fast convergence. However, if the weights are unbounded, they can be arbitrarily large, then the chain is going to be subgeometric. So it's not going to converge exponentially fast. So that's quite nice. But what we're going to consider today is what we did is we make this basically considerably more precise and transparent. We're going to precisely quantify, if you like, to what extent is it subgeometric? How much worse, in a pretty precise way, is it worse than the marginal chain? And the tool we're going to do that is a weak Poincare inequality. So before I talk about a weak Poincare inequality, let me first introduce the strong Poincare inequalities, because these are much more intuitive, I think, and they'll motivate the weak ones. So when we analyze convergence of Markov chains, we're going to be doing it in the L2 Hilbert space framework. So hopefully there's no surprises here. It's just the standard, in a product space of square integrable functions, where you integrate functions against a fixed measure mu. And of course, because we're going to be looking at convergence, we can just, without loss of generality, center the functions, we subtract their means. So we're just going to look at those and look at convergence to 0. And so the key object, which is going to recur a lot in this work, is the Dirichlet form E of P star P, which is a function of f, where f is a centered L2 function. And what is the Dirichlet form? It's relatively simple. It's the inner product of the identity minus P star P applied to f, then integrated against f. And I'm not going to give you an intuition yet. I'm going to move straight on to a strong Poincare inequality. So a strong Poincare inequality holds if you can find a positive constant Cp such that this Dirichlet form I've defined above is always lower bounded by this constant Cp times the variance. So if you can find such a Cp, which is positive, when this holds, you say you have a strong Poincare inequality. And why on earth would you care about this? Well, you'll care about this because if you have such a strong Poincare inequality, you immediately deduce exponential convergence of your transition kernels, right? And the proof of this is literally 3 lines long. So assuming you have a strong Poincare inequality, if you literally just rewrite it, you write out the definition of the Dirichlet form and push some things around, you can get to this stage here where you can say that Pf squared is less than 1 minus Cpf, and then immediately by induction, you can deduce the exponential convergence. So if you can show such a strong Poincare inequality you're in business, you can immediately write down this exponential convergence, which is great. But of course, I was saying earlier that we're interested in situations where the convergence is subgeometric. And so in that case, you can't use a strong Poincare inequality, right? Because if you have this, it has to be geometric convergence. So we're going to generalize this to expand it to allow us to derive subgeometric rates of convergence. And to do that, we need 2 key ingredients. The first one is a function alpha, which maps the positive half-line into the positive half-line, is a decreasing function, and it typically explodes at 0. So you can think it has an asymptote at 0 and then comes down and it decreases. So that's the first ingredient, a function alpha. The second ingredient is a function capital phi, which you can think of as a kind of penalty function on L2. I'm not going to go into the various conditions it needs to satisfy. I'll just leave that there for now. And so what then is a weak Poincare inequality? These are the 2 key ingredients. And I should say we were inspired by Röckner and Wang, who basically introduced these for continuous time semigroups. But we kind of took that and did the obvious thing in discrete time. And it says the following. So we need for all r, so every single value of r, and for all f, which is centered in L2, we need the following to hold, which is that the variance of f, because it's centered, needs to be upper bounded by this alpha function times the Dirichlet form, plus this penalty term r times phi of f. So let me try and give you some intuition. So the first thing, if alpha r is bounded above, it's capped by some big constant m, say, so we're not in the situation where it explodes. If it's capped above, you could send r to 0, right? The second term will vanish, and you'll simply have f squared is upper bounded by some big m times Dirichlet form. If you divide by m, you exactly have a strong Poincare inequality, right? So it does include the previous case. However, if alpha is exploding at 0, you can't simply send r to 0. Well, you can, but it won't, this second term will disappear, but this first one will explode. And the kind of example you can have in mind is where alpha is like r to some negative power, so explodes at 0, and phi is the oscillation squared, which is like the sup norm squared. So this is the kind of thing you can keep in the back of your mind. And it turns out a more useful, just a more convenient form of this weak Poincare inequality is to basically reparameterize it by taking essentially alpha inverse. So instead of having alpha of r, we just have s. And so r basically becomes like the inverse of alpha, which we'll call beta of s. But it's completely the same. And we'll call this a super-Poincare inequality. And in this case, because we've taken the inverse, now this beta is now a decreasing function, which goes down to 0 as s goes to infinity. And so this is the form that we're going to be working with, because this is more convenient, it turns out. Okay, so I told you before that this is going to give us subgeometric convergence rates. And here I kind of just splurged a bunch of stuff on the slide. I think I'm going to switch to the whiteboard now, basically to actually walk through where this all comes from. Hopefully this is all, you can all see this. Yeah. Okay, so what's the goal? So we're going to start from this super-Poincare inequality I wrote down a second bit, right? So it's s times the Dirichlet form, which I'll just write as E of f for convenience, plus beta of s times its capital phi of f. Right, this is our starting point, super-Poincare inequality. And we're just going to push some symbols around. So we want to find a lower bound on the Dirichlet form divided by phi of f. Right, so this is going to be lower bounded, so this f is on the other side, and we have to divide by s as well as phi of f. And then we're going to have to subtract the beta of s and then divide by s. So this just comes from pushing the symbols around. At this point, we're going to make a kind of substitution. We'll call u 1 over s, and we'll call a function k of u to be defined to be u times beta of 1 over u. Right, and with this kind of definition, if you like, this inequality, you can just rewrite it as this left-hand side being lower bounded by u times f squared divided by phi of f minus now k of u, right? Because this whole second term is basically just k. And this holds for all u, right? And so in particular, it's going to hold for the supremum, right? So this left-hand side is lower bounded by the supremum. So basically we maximize the right-hand side of exactly this, f squared phi of f minus k of u. And those of you familiar with convex conjugates will recognize that this is exactly the convex conjugate of k applied or evaluated at f squared over phi of f. This is basically the definition of the convex conjugate, which can be computed explicitly in various cases. I'll come to that later. And I'm going to call this inequality now a kind of an optimized super-Poincare inequality, which is going to turn out to be very important later. So now we've got this inequality, which we just got from massaging the super-Poincare inequality. I'm now going to define a new function called f of x, which is defined fairly abstractly as the integral from x up to a fixed constant a of dv divided by k star of v. And it turns out just by basic properties of k that f has the following kind of shape, right? So if you plot it against x, it certainly hits 0 when x is a, and it basically will always diverge to infinity as x goes towards 0. So it always has this kind of shape. This just follows some basic properties of k and k star. So why is this useful? Because f is going to be crucial to defining our subgeometric convergence rates. So now to drive that, I'm just going to write hn is just going to be the norm of pn f squared divided by phi of f. Right, so essentially what we want to know is how fast do these h of n's converge down to 0, right? Because remember, we want convergence of these PNFs to 0. So for starters, we can consider f of hn minus f of hn minus 1. It'll become apparent very soon why on earth we would consider this. Well, the first thing to note is that by definition of f, this is simply the integral of hn to hn minus 1 dv of k star of v, right? Because f is defined in terms of its integral, so it just looks exactly like this. K star is always monotone. That's just a basic property of K star. And so we can lower bound this by kind of the window, the integration window, and then a lower bound on the thing on the integrand. And the lower bound is just K star of the upper endpoint, h of n minus 1. Right, this is just using the fact that K star is a monotone function. Now, this is where the Dirichlet form comes in, because it turns out hn minus 1 minus hn is precisely the Dirichlet form but applied now to Pn minus 1 of f, also divided by phi, because the Pn's were divided by phi, and this whole thing is divided by k star of Hn minus 1. Right, so this is where we use the optimized super-Poincare inequality. Oh, sorry, I haven't used yet. I'm about to use the optimized strong Poincare inequality, super-Poincare inequality to lower bound this quantity, because remember this inequality concerns the Dirichlet form divided by phi. There's some extra steps in here because there's actually it should be a Pn minus 1f here, but I won't go into those details. This is lower bounded by the optimized super-Poincare inequality of k star applied precisely to Hn minus 1. Right, because if you like, this can be related to Hn minus 1 when you apply it to Pn minus 1. And this is lower bounded, and of course, you still have the same denominator. Right, so to go from here to here, we've used this inequality we derived. And of course, this is just 1. Right, so what this basically means then is if you string all these inequalities together, what you can say is that f applied to Hn minus, say, the starting point, h of 0, is at least n. And remember, we're interested in how fast these Hns go to 0. So if you just invert this relationship, it immediately implies that Pn of f squared is upper bounded by phi of f times f inverse of n. This just comes immediately from inverting this relationship. And so the intuition then is because, remember I said that this f function always explodes as you go to 0. So if you imagine you evaluated at n plus 1, f n plus 2, and so on, you could take the inverse and you'll see it has to go down to 0. Right, so essentially the rate at which this function explodes is going to tell you your convergence down to 0. And so I think I will switch back to the slide now. Where is it? There it is. Right, so I hope now you have some vague intuition as to where this f inverse comes from, right? And although I did it really fast, so you maybe didn't follow the derivation I just did, but that was essentially the entire proof, right? The entire proof of this subgeometric convergence rate was on that one slide I just did. In particular, at no point did we have to introduce things like small sets, atoms, split chains, none of that stuff. It was just a purely algebraic manipulation that took us from this super-Poincare inequality to a convergence rate. And I think that's one of the main reasons we think this is a cool framework to use, is because that derivation, I think, is really quite transparent. The first time you see it, maybe it's hard to follow, but it's really not that hard. Okay, so now let me give you some actual examples. So remember, this beta function is crucial. So if this beta is, say, going down like a polynomial, then it turns out you crank the handle in this proof I just did, and the f inverse is polynomial at the same rate. If beta goes down a bit faster, like an exponential, you'll get an almost exponential convergence rate in the f inverse because this exponent is less than 1. And the general intuition is that the faster this beta function goes down to 0, the faster the f inverses will go down to 0. And in fact, the situation where beta literally hits 0 and then it's 0 forever corresponds to exponential decay. So that case is also subsumed in this framework. And this technical point, I think I will skip. So now let me go back to the original kind of motivation we had, right, which is to compare pseudo-marginal chains. So just to remind you, we wanted to precisely characterize how much worse is a pseudo-marginal chain when you use some pi hat compared to the original marginal chain where you just had pi. Let me quickly give you some notation now. So P tilde will be the pseudo-marginal chain. Remember, we're doing random walk. And P is going to be the original random walk with pi and no pi hats. Although both are going to be constructed on this augmented state space, which contains the weights. Now I'll let pi tilde of x be a measure which is associated with these weights, which give rise to the pi of x. Remember, this pi hat is like w times pi of x. So this measure is associated with those weights w. So here is our main convergence result, comparison result. So here we have the Dirichlet form of the original marginal chain P, and here we have the Dirichlet form of the pseudo-marginal chain here. And you see what this is basically saying is that the pseudo-marginal chain is going to be worse than the original chain. How much worse? Controlled by this beta function, which we explicitly have written here, which is defined by the tail probabilities of the weights. So remember I said the faster this beta goes down to 0, the kind of better the convergence will be. And you see that is exactly aligning with the intuition that if your perturbations have a really fat tail at infinity, that means these probabilities are decaying slowly, so you expect a worse rate. On the other hand, if your perturbations have a light tail, so they're not too crazy, then this beta is going to go down faster, and you get a faster convergence of your pseudo-marginal chain. And so this, I think, is quite nice because it does really precisely give you control, depending on the tail behavior of your weights, to link these convergence rates. So now let me give some concrete applications of this. So the first one is to ABC. So I won't go into all the nuts and bolts of ABC. I'll just say in this setting, we have, a posterior with a true likelihood Ly, but this is horribly intractable for reasons. And so we're going to work instead with the ABC posterior, where we take the original prior, but we replace this true likelihood with the ABC likelihood, which is this probability that Z is close to data, where Z is like fake data you generate, and you ask, is Z close to the true data? And you look at that probability. But of course, this LABC is itself intractable because there's no way to calculate this probability. But what you can do is approximate it using simulation, which exactly corresponds to a pseudo-marginal approach. And when you do pseudo-marginal targeting, this ABC posterior, you have a choice, which is how many simulations you do at each step, and that's capital N. Right? You could just draw one set of fake data, or you could draw lots of fake data, and that will give you a slightly different estimator. And so here I've defined what this W is exactly. But here's what we can actually say, which is that depending on the regularity of the prior, so in other words, how quickly the tails of the prior decay will tell us, what exponent will have a finite quantity here. You could always take P equals 1, because then this is just 0. But if your prior has, very nice tail decay, you could potentially take a higher power of P here, but you could always take P equals 1. And that value of P there is going to give you a bound on the convergence of this beta term to 0, right? So this beta term is going to converge to 0 at a polynomial rate, P, given by, the degree to which you can integrate the likelihood or the inverse of it with respect to the prior. The other nice thing this result says is it also tells you how N is going to affect the algorithm. So because we have this large constant CNP, and the way CNP scales with N is like 1 plus order of 1 over N. So what this is saying is you could use loads and loads more fake data at each step. That won't change the ultimate convergence rate of the algorithm, but it could potentially give you a much better constant at the front. And so we think that's quite nice because I think that is quite useful to know. And so yeah, and the convergence rate is always going to be N to the minus P in your MCMC. One final application then before I wrap up, which is something we could say about PMMH, which again, I'm not going to go into the details of that, but it's a well-established MCMC algorithm, which allows you to do inference, for example, in state space models. And we study the particular limiting case when the weights in PMMH are actually from a log normal distribution. And the kind of situation where this could arise was studied in this paper of Berai et al. And in that case, we could derive the following bounds on the convergence rate of PMMH, which is to say that this F inverse is exactly the convergence rate. So I've skipped past the beta and all that, and here's just the final convergence rate, which is a bunch of constants. So we're assuming that the marginal chain has a strong Poincare inequality with constant CP. Then the pseudo-marginal chain converges like e to the minus w squared, where w is the Lambert function. So that's the inverse function of x e to the x. So it's the Lambert function squared applied to basically n and a pile of constants here. These are just constants. And so this convergence rate here, because it's e to the Lambert function squared, is faster than any polynomial, but it's still sub-exponential. So yeah. And the other thing that we can do with this is we can basically optimize this as a function of sigma, right? Because sigma is related to the variance of the weights, which you as a practitioner could control by basically varying the number of particles and steps you use. And so in particular, we could say, if you want to say minimize the asymptotic variance, you can try and minimize that over sigma, and just numerically plotting the kind of expression you get a nice curve like this, which is minimized around 1, which is consistent with existing kind of tuning advice for PMMH that was in the literature. So I think I'm very much, about finishing now, just about out of time. So I'll just, wrap up by saying, so the paper is on arXiv. You can certainly go check it out. And we think this is quite a nice framework to studying various things like this. And there's still, I think, lots to be done using this framework. We're looking at things like lower bounds and connections with existing methods at the moment. So I think it's an exciting new development, and I think I will stop there. Thank you very much for listening.
Great, thanks, Andy. I'm going to stop the recording now.